Hi everyone, this is video going over an introduction to Chapter 3, and Chapter 3 is going to be dealing with graph theory. So graph theory is this broad branch of mathematics that deals with things that can be represented by vertices and then edges that connect them, right? So here's an example of a graph, and you could think of the kinds of problems that you could solve using this graph or represent using this graph. This could be a connection of computers in a network, or this could be possibly a electrical wiring diagram, right, where you could have each of these pieces might be a wired connection, or maybe there's capacitors and things like that in here, or this could be a plumbing diagram. I looked up some of the other applications of this type of thing in architecture, and I found a paper that would talk about a situation like this, where we'd have, let's say, a floor plan, and maybe it looked like this. And actually, I'm going to make this a little bit more interesting. Just so I can draw a graph in here. So let's say maybe this is a side closet or something like that. But if we think of this as being the floor plan, and we place a dot in each of these rooms here, and we can even consider the outside, right, the outdoors as being a room in this floor plan, then we can make a graph representing that. And the idea is that you can compare similar floor plans by comparing their graphs in here. I've also seen some applications where they deal with structural integrity, but that's going to be something I'll mention in person if you're interested about it. One aspect of this graph that might be a little bit new to what you've seen with vertices and edges before is that I'm drawing these kind of like weird curved shapes, and that's actually allowed in a graph. So as an example, if I draw this graph, right, this graph where I connect the pieces like this, I've got 1, 2, 3, 4 vertices and 1, 2, 3, 4 edges here. That's actually exactly the same as this graph here, where I give maybe some curved lines that sort of connect this in the same way. And so I can move the vertices around, and I can make the edges whatever shape I want. So that's sort of the freedom of graph theory. Really all we're interested in is what vertices are connected to other vertices. So I'll go ahead and write down some definitions here. But I can say a graph. A graph is a set of vertices and edges where the vertices are connected by edges. So we do need to define edges now in graph theory. So an edge, right? We could either draw them as line segments, or we can draw them as these curved lines, right? We have that freedom. An edge is a connection of exactly two vertices. Okay, so in this example here, I can label this vertex as vertex 1, vertex 2, vertex 3, and vertex 4. And I can label these edges E1, E2, E3, and E4. We'll see a little bit later that this labeling numbers really doesn't matter, right? So for example, if I make a similar graph with different numbers for each of these edges, if I put them in a different order, that would be what's called an isomorphic graph, which is essentially a congruent or a similar graph, right? It's the same graph in many ways. Okay. So as an example, if I want to talk about this edge, E1. So the way that we would represent E1 is, since it's connecting vertex 1 and vertex 2, we would say that E1 is the set of the two vertices V1 and V2. And then we can continue there, so E3 would be let's see, V2, V3. And we don't distinguish between what the start and the start and finish of those edges are. So E1 could also be written as V1, V2, or V2, V1. And this one can also be written in this other order. But each time it's only connecting two vertices, right? It's got two vertices that are being connected there. These are not the only types of graphs that we can draw. So I'll show you some other types of graphs so we can classify them. Okay. So here's some types of graphs. We've got a multigraph. So a multigraph, I think this will be best demonstrated. You can look up the definitions in your textbook, but I'm going to draw pictures because I think that's the most illustrative thing I can do. This is a little bit different than what we've got here because we've got two edges. So I can say multiple edges. Oops. Multiple edges. Connecting the same two vertices. So if I give these the same set of labels, if I call this V1, V2, and V3, and I call these edges E1, E2, E3, and E4, then I could say that E1 and E2 make this a multi-graph. So So two edges, same set of two vertices that are being connected. So we've got multigraphs. We've also got pseudographs. So So this still counts as a graph. This still counts as a graph. If we have a graph that looks like this. So now if I label these vertices, right, and call this V1, V2, V3, and call these edges. This one does count as an edge, right? So E1, E2, E3, E4. Okay, so if you think about how we would say, well, you said that an edge has to connect two vertices. It is still connecting two vertices, they just happen to be the same vertex, right? So the way that we would write that would be the E1 is just V1 connected with itself, V1. Right? So this is still a graph, but it is what we would call a pseudograph. Okay. Another type of graph would be a complete graph. So a complete graph, I'll give you an example of a complete graph. This is a complete graph. And the reason why this is a complete graph, once I finish it, is because every vertex is connected to every other vertex. So we've got 4 vertices here, and there's no missing connections here, right? Like I can give these labels again. V1, V2, V3, V4, right? 1 is connected to 2, 3, and 4 by an edge. 3 is connected to the rest of these, and so on, right? So the name that we give this, we call this one we would call this K4. So K little 4, because it contains 4 vertices. So I'll go ahead and draw some other K1s right here. So K5 is going to become, so this graph here is K4. K5 looks like this. Right. Here's K sub 5. K sub 2 is not very interesting. Here's K3. But all of these are complete because every vertex is connected to every other unique vertex in that. Okay. Before I talk about the other types of graphs, because we've got 2 more that I want to talk about, I want to talk about this idea of valence, just so I'll introduce it, and then we can talk about that in the context of all these. Valence is a measurement of how many edges are coming out of a particular vertex, or how many edges are contained by a particular vertex. So if I look at this graph here, V1 would have a valence of 2 because we've got edge 1 and edge 2 coming out of it. vertex 3 would have a valence of 1, 2, 3 because we've got 3 edges coming out of it. I am not counting things like this as vertices in this graph. Sorry. I'm not counting connections like I showed there as vertices in here, right? Only these dots that I've made here, right, count as vertices. So we'll talk about how to undo those. But in a complete graph, right, we can see K5. I'll say each vertex so they all have the same valence. And this one has a valence of 1, 2, 3, 4. This vertex has a valence 1, 2, 3, 4. So all of these have a valence of 1, 2, 3, 4. This one, each vertex has a valence of 1, right? It's just the 1 coming out of it. Each vertex has a valence of 2 here. So in general, we can say that, what's the pattern here? The vertices in a complete graph Kn, right? So K, some number, will all have a valence of right, 1 minus, or n minus 1, 1 less than that, because it's got to touch, if there's 5 vertices, we've got to touch, each one has to connect with all the other 4 of them, so just 1 less than the number of vertices in there. We denote the valence of a vertex using Q, right? This letter Q. So we would say something like Q of V2 is equal to 3 means vertex 2 has a valence of 3. Okay, so those are the big concepts from the first section. I want to talk about those other 2 types of graphs. So we've got complete graphs where every vertex is connected to every other vertex. We've also got complete bipartite. So complete bipartite graphs are 2 sets of vertices. And I'm going to give them the names left and right. Where each left vertex is connected to every right vertex. But there are no connections between the left vertices and no connections between the right vertices. So probably better to show you this in by way of example. So the name we would give to this graph, so I've got some left vertices and some right vertices. So this one's got to be connected. If it's going to be a complete bipartite, this one here needs to be connected to every vertex on the right. Right. Same thing over here. So this would be a complete bipartite, and we would label this K 2, 3, because there's 2 vertices on the left and 3 vertices on the right. We don't need to have a mismatch between them, right? We can say something like, right, K 4, 4, and as long as every connection from left to right is made, so a good way to check to see if we've done everything right is to use that valence, right? So each of these points, let's think about what the valence might need to be to see what we're missing here. Well, look at this. Each point over here on the left has got a valence of 3 because it's got to connect to those 3 points. And each one over here has a valence of 2 because it's got to connect to each of the 2 left each of the 2 left vertices. So for this complete bipartite, each of these vertices should have a valence of 4. So let's make sure that we've got 1, 2, 3. Oh, no, we need 4 here. Let's see. This one only has a valence of 2, so we should be missing 2 of them. Here we go. All right. So quite a web that we've made here, but this is a complete bipartite. So you can notice the vertices. The numbers in the subscripts. Okay, so this word complete means that we've got sort of every connection covered. but we do have just simply bipartite. So these would be, just to be clear, these are not complete. Right. But they still have that same structure. So let's use that same setup here where we've got 2 and then 3. Over here I can make these connections from here to here. And then maybe I leave one of these connections out, right? So it just looks like that. So it's not connected to, well, let's maybe give it one more. Right? But since we don't have this connection between these two, since there's no connection since we're missing this edge here, the bipartite graph is not complete. Okay, the name that we would give this one, we wouldn't use K. K we use only for complete graphs, but this B here, we could still call this B2 and 3 because that is the number of vertices on the left and number of vertices on the right. Okay. Those are all the distinctions that I can make here without sort of showing some movement on here. But make sure that you are able to answer true and false questions, right, about complete bipartite and complete graphs, multigraphs, things like that. This next one, this type of graph that I want to show you is something that's called a, one second. Sorry, I've been having trouble getting this to retain this size on here without hacking it. Delete all that empty space that I make. Okay. Now we can talk about planar graphs. So planar graphs these are graphs that can be written and can is kind of an important word in here, that can be drawn such that no edges overlap. All right. So if I have a graph that looks like this. And I've got edges that look like this. I can say in this arrangement, the edges overlap, but this is still a planar graph. Right? And the reason is because it can be drawn such that no edges overlap. So if I erase this and if I just draw one of these edges in red here, I can demonstrate. Again, there is no difference in graph theory between this connection and this connection, right? Graph theory says that these are the same connection. So when we look at these, when we look at this graph here, we can, hopefully let me copy this. Okay, guess not. So we can draw this graph. We can convert that and just move this one edge so that it moves around that the rest of the graph, and it won't overlap anymore. So then we can say the graph is planar, right? So So I managed to redraw that graph to show that it is a planar graph. Now, we're going to have to think about moving edges like that. We'll actually have some ways to figure out if something is planar or not without having to move these edges around or kind of make these curvy lines like that. Anyway, that'll be in the next video, so I'm going to stop this one here and then talk about the rest in the next part.